Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about NavIC is dead. Basically, India lost its own satellite navigation system. So what the heck happened? So let's dive deep into it. Now you have to understand NavIC, our puppy. This was a result of bitch slap from USA. So basically we got bitch slapped in Kargil War in 1999. Basically they shut down the GPS. Yes, we had paid for it. Yes, it was a military agreement and they just turned it off. Basically they did not want it boom boom to become nuclear boom boom. That's what they said, but at least we realized that even if we are paying, even if it's a weapon system, it can be turned off by someone else. Basically someone else has a remote control for a sensitive system. So we learned the hard way that thou shall not buy war technology from someone else. Therefore, NavIC was created. NavIC got green light. Basically, government was working and ISRO was creating plans for it. That happened in 2006. And it was given 1420 crores. That was a decent chunk of change back in that day. And the idea was while every other player, basically Soviet Union or Russia at that point in time, Russia and USA and European Union and China, they were all planning to make their own system, but they were directly targeting global. Now, you have to understand, right now India is swimming in money, but in 2006 it was not that great. So it was like, okay, we have to do multi-pronged attack here. So the idea was two-stage rollout. First stage you take care of the country, second stage you take care of the globe, meaning first focus on providing navigational services in India itself. After that, go YOLO. So that was the attack plan, and India will make that system, including the receiver. We had learned that from BitSlap. If we are making satellite, again, India had the capability of making good satellites. We had done it for a long time. If we had the satellite and we are buying microchips from China, China could just like lol during wartime. So we learned the hard way. It's like we'll also make the receiver IC itself. And it got funded and priority from cabinet, meaning no matter what happens, this will not be closed. The project will not be shut down. You have to just go YOLO on it. And India must have this for its sovereignty. Like we really can't rely on something as serious as navigation on someone else. Right now we do have multiple system that works with multiple system, but having something that you can trust, rely, absolutely trust, like this is something that is like, the final say on a weapon system, that's good. So the deployment of this was done differently. The target was creating this patch. They were not targeting the whole planet, just this patch. The patch is whole of India and then 1500 kilometers outside of the border, the buffer zone, basically where the actual conflict will happen. To give you a context, that covers the whole Pakistan, meaning we can send soldiers to the furthest corner of Pakistan and we still be inside the coverage. Whole of Nepal, Bangladesh, even Myanmar and all that. Like we got this. We good. Even a large section of basically naval assets, they got this. Like almost Strait of Hormuz is covered, by the way. That's how far it goes. That 1500 kilometer buffer zone, it's huge. So we got this. Like we got this. And over time, the idea was we're going to expand from this sort of patchy coverage to planet-wide coverage. And we chose a different approach. The approach was, rather than going into medium Earth orbit or low Earth orbit, we're going to go for geostationary. We're going to go further. Why? Well, it simply allows us to achieve functional system with very few satellites. America had to launch a lot of satellites before they got their first receiver to work. We did not want to have that scenario. That was the whole point of two-stage rollout. So idea was we can get functional as little as 4 satellites, and we will have like full coverage and quality of service very high if we have only 7 satellites. And again, 24/7. So that was the aim. The area of interest would be covered by geostationary orbit. So basically we'll have something in 55-degree inclination, another in 83 degrees Celsius, I'm saying, degree inclination, another would be 117.75 degree. So basically we're going to have full projection on Earth, India, and to make sure the satellite does not face shadow issue, all the satellites have a bit of an elliptical orbit. Figure 8 orbit. So benefit is like if they were all put in an exact fixed spot, they will barely have any latitude, so to say. So from ground point of view, they will be too easily blocked, even if you are going like a little bit of shade. So you do want your satellites to have a bit of oblique angle, if I'm not mistaken, that's the term, to make sure that satellite can penetrate. So having this sort of figure 8 scenario allows us to have like full coverage, where it's like, oh, if you are in a little bit of valley, your satellite signal will not work. No, we're good, we got this. And again, Earth is not flat, it's a sphere. So we do need to have some compensation. That's how it works. And only 4 satellites would be needed to cover area of interest 24 into 7 into 365 without any issue. And if you tried with LEO, it would require way too many. Even MEO, medium Earth orbit, 20,000 kilometer plus, that would require 24 or more minimum. So that's why this approach was chosen. Geostationary satellites and few satellites, we good, we got this. Whole India will be taken care of. So how the heck does satellite math works? Now, today was the day when I understood it, like not the math part, but like, okay, what are you doing? Because here's the problem. You can't tell a distance from a beacon. Like if you are seeing a lighthouse, you can't tell how far the lighthouse is. Like how does a radar work? Radar screams, it's like, bah. It screams, the radar radio waves comes back, and then you stop your stopwatch. And now you divide the distance by, basically divide the time by 2, one way, and then you multiply that with the speed of light, and tada, you have the distance. Satellite is not screaming like that. Satellite is just a beacon. It's just like blah, blah, blah. It's not waiting for your object to send it back. There is no two-way communication. So how the heck you do that? How the heck a mobile phone, this puppy, can receive and tell where it is? It can't. It can see the satellite, it can receive the signal, that's cool, awesome, GG, but it can't tell the position. That was the problem with GPS. How the heck they're gonna solve it? And they figured out a very clever mathematics. Somebody was on some good shit. And if you have 4 satellites, they can tell you precisely without requiring atomic clock on your side. If you have atomic clock on your side, you can get around with 3. So the idea is every satellite screams, and that scream has few data points. First data point is what satellite number it is, like where it is, and what time it is. So its orbit, where I am in this orbit, and what is the time. So these are the 2 data points. That allows, basically that location where it is in the orbit helps the math to narrow down possibility. So if you're getting jamming or error, something basically interfering with it, you can deal with it. So UTC time, that's the actual bread and butter, or extra data just to make sure that your math becomes clean. And you use microsecond level short-term accuracy. Now here's the deal. The oscillator that is on the atomic clocks that are on the satellite, those are nanosecond level or even picosecond level absolute units. They're good, they got this. This puppy has an oscillator. Oscillator drifts like crazy. It's not accurate enough. However, that accuracy is absolute accuracy, meaning if I set this time to atomic clock, how far it would have drifted in 1 hour? A lot. However, how much it would have drifted in few microseconds? Very little. Oscillator takes a sweet time to drift. It does not go from, oh, I was vibrating at that speed and randomly changed. It's very stable in short duration. So technically, you can achieve microsecond level precision. But assume this is 1960s or 70s. You don't have even microsecond, you have millisecond level, which again we achieved millisecond back then. Heck, your clocks have millisecond. So what does it mean? Like if you can sync, basically you wait, okay, my satellite screamed, this is the timestamp, cool, I will wait. Now the second time scream that satellite is screaming, that will come to me, but again it will be bit delayed. It won't come because again it does take time to Alex. So I'm waiting for 1 second for next signal. The next signal will come bit later. I set my time according to it, the oscillator time, according to it, but it took bit later. That bit later will allow you to be accurate enough in milliseconds, not micro, milliseconds. Now you can guesstimate your position in 300 kilometers. Now that may sound bad, but that's more than good enough, because you are talking from 20,000 kilometers to 300 kilometers plus and minus. That's good. We got this. And this is where the mathematics happens. And that's why you keep hearing the term 4th satellite or the clock satellite. So that's what you do. Your oscillator short-term accuracy is good enough to do mathematics on a microsecond level, and mathematics is strong enough that it can work on millisecond level. Millisecond simply means you're going to be off by 300 kilometers. Microsecond means you're going to be off by 30 meters. You could be on a different block. So how the heck you go down to meter level? Well, here's the deal. You do mathematics. That's why 3 satellites is bare minimum if you have what we call atomic clock on yourself. You draw 3 spheres from the satellite. Basically, whenever you are listening distance from a satellite, all you are listening how far I am. So satellite A, you are the object, but where are you? Anywhere in the sphere. Now Earth is a sphere, so this will become a circle. You can be anywhere in the circle. Not useful. But now you do this with 3 things. So now you're making 3 spheres. 3 spheres can only intersect at 2 points. Now, Why that will be enough? Well, here's the 1 point would be ghost point, meaning it will be either in hell or in basically heaven. So 1 point, it will show that you are somewhere in the 40,000 kilometer from sea level. Another would be on the sea level. So most likely the sea level one is the correct one. That's why I said 3 ones. But again, that's still sloppy. Assume your microsecond is that the data point is still not that good enough. So how the heck? And again, this puppy does not have an atomic clock. So what do? Well, you add one more sphere. Now here's the mathematics part. If you have 4 spheres, they can only intersect at 1 point. Physics will not allow 4 spheres to intersect at multiple points. Like 3 still interferes at 2 points. So having 4 removes all the mathematical ambiguity. Now you apply the magic of mathematics. Now you know what you're supposed to get. You're supposed to get a point, dimensionless point, like this point is it. So you backtrack the mathematics, meaning you feed in the sloppy data from milliseconds into equation like this, which is what we call least square theorem. So now you back solve it. And how do you back solve it? You basically, I put this data. Okay, what if I increase the time? Now your error is a sphere. That sphere must contract. That means you are getting precise and precise. If it's expanding, yeah, bad. Okay, change the time in this direction. Okay. You basically are shrinking, you're expanding it first, then you're decreasing it, then PID loop. Almost a PID loop it is. Again, mathematical, but now you're allowed to solve for time delta. Once you have the time delta, now you know exactly within meter square. Like, I am here without requiring atomic clock. That was the brilliance of the people who came up with this. That was good. Like, somebody was on good stuff. It's like, it's transferring satellites accuracy, meaning when this calculation is finalized, and when the mathematics is done, at that point, the time data, because you never had the time data, it actually behaved like your mobile phone had atomic clock. That's why it needs 4. Now, be mindful, 4 is bare minimum. Your modern systems assume 5 or 6, what we call dilution of precision. You should have multiple satellites. Once you have multiple, it is accurate. And once you have a good enough timing data with a fixed data point, you can be sub-centimeter accurate. So that's the mathematics of basically your mobile phone, if it's a millisecond grade accuracy, it still creates a bubble. That bubble is almost like, 300 kilometer sphere. How do you shrink the sphere into a small one? You apply mathematics. You tell the mathematics, bro, I'm getting this distance, allow me to shrink it. Because of the mathematics, there should be only 1 point. You solve the mathematics, you oscillately solve it. Now you know. So that's how it works. That's how it quote unquote transfers the satellite time into your mobile phone. That equation is the key. That was the hardest thing to understand. It's like, I get the millisecond part. Your mobile phone should be able to tell in that. But like, that's 300 kilometers. How the heck you know in meters? So that's the mathematics part of it. That's why you need 4 of them. India just lost 1. So now we are down to 3. Meaning our missiles, if it has a very good oscillator, it should be good enough. And our naval vessels, if it has onboard atomic clock, which most likely it does, we should be good enough. But almost every civilian application kaput. And even those military application is what we classify as degraded state. It's not dead, but degraded. So how the heck this sort of failure happened? Well, you have to understand this. ISRO, while we do take pride on it, we take pride simply because it's the least corrupt one. ISRO really did not took this project seriously. And again, this is not me saying it. This is not my personal opinion. This is from this daddy, Supreme Audit Institution of India. Basically like how NASA has NASA's Office General Inspector. Like basically who sees how the heck NASA is spending money. This daddy is responsible for that. It's like how you're spending the money. We gave you the money. Where did the money go? And they come up with an audit report in 2018. And let me compress that hundreds of pages of data. It's bad. It's bad. Like bad. So here's the deal. The satellite was made. Cool, awesome. India knows how to make satellite. GG. We put 3 clocks. GG. Backup. GG. Yeah, we forgot the core rule of backups. No dissimilar redundancy was there. You should always have dissimilar redundancy, meaning you should not have, I have this atomic clock, now I'm going to buy 3 of these atomic clock. That should not happen. You should be like, okay, I bought atomic clock from this, I bought atomic clock from that, I bought atomic clock from this, make one in India. Now you have dissimilar redundancy, meaning you are immune to what we call common mode failure. And we did not do that. Like that's the fundamental design. That's a concept. Like you can type it. Like if, for example, let's just say you are making a server and you're like, I want to make sure the operating system never corrupts. You do not buy SSD from the same brand. You buy one SSD for, let's just say, Western Digital, another for Crucial. So you can make sure that there are 2, or Samsung. So now you can be damn sure there are 2 different scenarios. where it's like one thing should not kaput both of them. And again, it's a mathematical concept, like everybody should know this, dissimilar redundancy. And to give you a concept, like this is not just me saying it. America did not do that simply because they were the first, they were figuring things out. But why Galileo happened, Galileo had hydrogen maser as their primary clocks. The second clock is rubidium clock. And even Russian systems, which again, they were very, very closely copy-pasted from American system, they also had that issue. But again, even they learned it's like, okay, we're going to have rubidium and we're going to have cesium. Nobody puts one thing 3 times. That's useless because you are vulnerable to common mode failure. And what happened? Whoever made up that batch messed up really badly. One capacitor had some issue and kaput. All satellites, kaput. So this was the really big issue. Like that, this was just mathematically bad. I get it. Like satellite bad, like clock supplier bad. That is factually true. But that should not have crippled India's national grid level project. It's like, no, this should not have happened that you have 3 of the same item from same supplier, same brand. I'm like genuinely worried. If I really dive into it, it might be from the same batch. They may not have even randomized the batch. So this was failure. Again, I get it, you got a poor supplier, but again, that's why you, for national security level assets, you always have second supplier, always have second source or third source. This was just dumb. So what can we expect in the future? Well, reality is we should be able to get back on our feet soon, hopefully, trademark. My expectation is before the end of 2026, hopefully. And again, now we have figured out how to make our own atomic clocks. And again, it is doable. We know how to make satellites. These things have been working. So we got this. We should be doable. However, the weak link is not the satellite nor even the atomic clock. Although I genuinely hope they are still making sure they do not have the same hardware 3 times. ISRO rockets are the weak link. While ISRO had a very good track record, these 2 boom puppies, they really ruined it, so to say. C62 and C61, both of them went to boom, which is very rare because PSLV is a workhorse of ISRO. It has flown more than enough time, hundreds of time, that it's like we don't think about it. We don't cover it because it's like, bro, it just works. But one boom happened, which again, fine, things happen. Second boom happened exactly the same way. Common mode failure. That was bad. So basically fourth, I think. Fourth upper stage is having issue in both launches. So that's a very serious doubt on reliability because be mindful, this is the most launched rocket from ISRO. Having fault in this is first frustrating. Second, having 2 launch back-to-back going boom is really, really bad. So, and this is no longer capable enough to lift our basically NavIC Mark II satellites. Those are a bit bigger, more beefier. They require GSLV, Geostationary Satellite Launch Vehicle. So GSLV, we don't launch enough of it. This is like, when it was working, it was like this once in a while. So I do expect ISRO to struggle a bit, not from the satellite point of view, not even the atomic clock point of view, but like, do we actually have a rocket that we can trust to put the satellite and launch it? So I just hope we need to learn thou shall not have single source backups. Like that is like, that's not a backup, that's hope and pray. Like even for data guy, people tell you 3 to 1, 3 copy of data, 2 medium. It must be on second medium. For example, if you are having all the data in hard drive, have one in SSD, or in my case, have one in optical disk. So have some dissimilarity. So all of them does not fail at the same time. So that has to be learned. That has to be core learning. And again, I'm a bit worried if we keep using the same philosophies, like, okay, just put 3 of them. It's not good enough. Global coverage is very far away, not from the satellite point of view. I think we got this, we can do that. It's just the rocket is not good enough. The launch cadence is not fast enough. And again, these 2 made the whole launch cadence 0. It's like, nope, figure out what the hell happened. And lack of private launches is really hurting it. And this is a military grade system. And again, national security, it's unlikely that we're going to send it to someone else like SpaceX to launch it. So let's see what happens. But again, it was a very embarrassing failure. Again, I'm really not telling you what all messed up happened in that 2018 report, but it was like, damn. Like I thought SLS was bad. So this was my presentation, what the hell happened and how the heck the mathematics, so why do you need 4? So I hope you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.